This is a section that you should have learned in Chem 1A. But because you probably don't remember it very well, or maybe you weren't exposed to it at all, we're going to cover it here as well. Redox reactions, oxidation-reduction. So there's different ways to remember which one is oxidation and which one is reduction. And this is another area in chemistry where you have two things and you have to figure out how do you pair them up, right? And so you could flat out memorize it. That's never really worked for me. I need to have some, mnemonic or some strange explanation in my head so that I can remember them. So a common way people do this is the phrase or the two words, oil rig, right? So that stands for oxidation is loss of electrons, OIL. Reduction is gain of electrons. Oil rig. So that's thinking about it in terms of the electrons. We can also think about it in terms of oxidation state. And this is where the words actually came from. So an oxidation results in an increase in the oxidation state. A reduction is a decrease or a reduction in the oxidation state. Okay? So here, calcium has an oxidation state of 0, and over here it's going to have an oxidation state of +2. So that's an increase in the oxidation state. Here, hydrogen is +1, and over here, hydrogen is 0. The oxidation state has gone down. That's reduction. We can also think of this in terms of oil rig. How does a calcium atom become a calcium 2+ ion? Something happens with the electrons. Right? It loses 2 electrons, and that's how it gets the positive charge, right? So oxidation is loss of electrons. And here, the hydrogen technically doesn't have a +1 charge, but you can think of it that way. +1 to 0, that would be gaining an electron. Reduction is gain of electrons. So when we have a redox reaction, an oxidation-reduction reaction, we always have oxidation coupled with reduction, because one thing is losing electrons, the other thing is gaining electrons. And so to balance these reactions, we can't always just use the balance by inspection, just looking at them method. Sometimes that works, a lot of times it doesn't. That will balance the mass. We'll have the correct number of atoms of each thing on each side, but we also need to have the charges balance. So the book is teaching us what's called the half reaction method for balancing redox reactions. And so the plan here is we take that equation and you separate it into 2 half reactions. You balance those separately, and then you put them back together. Okay? Brief review of oxidation states. So there's a set of rules, and they're in an order of priority. And like rules to a board game, when you write down all the rules and try to read them, especially if you've never played the game, it's so confusing, right? Like, what are they talking about? And that's what happens when you write down things for like rules of oxidation states as well. They become pretty confusing. If we can step back and see what they're actually doing, it's not that hard. So a lot of times the oxidation state will be the same as the charge on the thing. What's the charge on a free element? 0. It's neutral. Free elements have an oxidation state of 0. So Na is 0, Cl2 is 0. They're elements, no charges, oxidation state 0. If we have ions, single atom, like sodium ion or chloride ion, they have charges. The oxidation state is the same as the charge, right? If we have an ionic compound with a bunch of ions in it, we learned that all of the charges have to add up to 0 to make a neutral compound. The same thing happens with oxidation states. The oxidation states have to add up to whatever the overall charge of the thing is. So if we have a compound like NaCl, the overall charge is 0. That means that the oxidation state of sodium and chloride have to add up to 0. If we have a neutral molecule like H2O, they have to add up to 0. If we have a polyatomic ion, this is more than one atom, but they're bounded together, and all together they have a charge. Then the oxidation states of all of the atoms in there have to add up to the charge on the ion. So an example here, nitrate ion, NO3 minus. In this one, the nitrogen has a +5 and the oxygen has a -2. So we've got 1 +5, we have a single +5, and then we have 3 -2s, right? So 3 -2s gives us -6, and you add 5 and you end up with an overall -1, which matches the charge. Everybody okay with that? This one I think is a little bit silly, but in compounds, metals are going to have positive oxidation states. In compounds, metals have positive charges, right? I don't even know why we need to say this. So group 1 metals are always going to have an oxidation state of 1, +1. What's the charge of a group 1 metal ion? +1. Group 2 metal ions always have an oxidation state of +2, which is the same as their charge, right? So this is the one part where we really need the rules and the idea of oxidation states. In compounds, nonmetals, what are they doing? So if it's in an ionic compound, that's easy. It's the charge on the ion. Like magnesium fluoride is an Mg2+ and 2 F minuses. So the charge and the oxidation state are the same. But what about when you have a molecular compound where there aren't any ions? And that's where oxidation states are useful. They're kind of like a pretend charge, so that we can look at what happens to the electrons. So these are the rules for oxidation states of nonmetals, and you look at that table and you're like, sheesh, how do I remember that? Do you know what pho is? Really good noodles, right? So if we just took a little bit of that P off, whoops, that's not what I meant to do. I lost. Okay, I'm just gonna start over. I don't know what's going on here. P, H, O, pho. And then if we cut off a bit of the P, it's an F, which is fine because that's the sound it makes anyway, right? Pho. So can you remember pho? F, H, O. 7, 6, 5. So pho, 7, oh gosh, 7, come on. 7, 6, 5. Yes, there's actually a restaurant, pho 7, 6. So they just need to put a 5 at the end, and they're going to be my cheat sheet for oxidation states. Okay, pho 7, 6, 5. You can remember that? Okay, if you can remember that, the rest of this is a piece of cake. So the letters here and the numbers give us the order of priority for the nonmetals. So the way I think of this is there's no charge in this molecular compound, but what would this atom like to have as a charge if it was an ion, right? What would fluorine like to have if it's an ion? -1. We learned that because group 7 is going to be -1. What charge does hydrogen have if it's an ion? +1. How about oxygen? -2. The group 7, other than fluorine, are also going to have -1. Group 6, -2. Group 5, -3. So the oxidation states here are the charges that that nonmetal would have if it was an ion. We already learned those, okay? So the only thing we have to learn here is what order. So, you've got carbon and oxygen together in this molecular compound. Well, carbon's like, well, I guess that's a bad example. Let's maybe look at H2S. So we've got hydrogen and we've got sulfur, and the sulfur wants to be -2, the hydrogen wants to be +1. Sometimes they both get to have what they want, and other times they don't. Who gets to pick first? Who gets the charge that they want? This is the order, Fa765. If fluorine's there, fluorine gets to pick first. Fluorine always gets to be -1. If hydrogen is there, it gets to be H+. Oxygen gets to be -2. Then you look at group 7 nonmetals. They get to be what they would have as a charge, 6 and 5. See how that works? So the oxidation states match the charges of these ions, of these elements when they are ions. Fa765 just tells us who gets to pick first. Because sometimes you have a situation where this one wants to be -2 and that one wants to be -1, and they can't both have what they want. So the list of priority tells us which one goes first. So any questions about that? Let's maybe just do one quick example here. So CCl4, nonmetals, no charges, molecular compound. But we can predict oxidation states, which are like imaginary charges. So we've got chlorine, we've got carbon, and we've got chlorine, right? So we think to ourselves, Fa765, are there any fluorines? Nope. Hydrogen? Nope. Oxygen? Nope. Group 7? Yeah, chlorine's group 7. So chlorine chooses -1. And there's 4 of them, right? Each of them gets to be -1. So this will give us a total of -4. This is a neutral molecule, has no charge on it. The oxidation states that the atoms have to add up to 0. So if the chlorines together are -4, what's the carbon? +4. Okay? It's so very much like charges. But we have to remember they are not actually charges. They're made up, but they're made up to help us understand what's going on. Any questions? Okay, so this is the procedure, the steps for the half reaction method. This is what the book teaches. It says assign oxidation states. That's actually optional. You can balance the half reaction without identifying any oxidation states. So you can skip that if you want to. Separate the overall reaction into 2 half reactions. One will be oxidation, one will be reduction. I don't care if you recognize which is which. We're just trying to get it done, get the thing balanced. Okay, so we're going to balance each of those half reactions in a very specific way. First, we're going to balance for mass. This is the regular kind of balancing. So you're going to look at all of the elements besides hydrogen and oxygen, and you're going to get them balanced by putting coefficients in. Then you're going to balance oxygen. What we'll see is a lot of these, there's like an oxygen on one side and the other side doesn't have any oxygen. You're like, how can I balance that? Well, the equations that we're trying to balance are net ionic equations, and they don't show everything. All of these things are happening in solution, in water. So if we need oxygen somewhere, we can just throw H2O in there because everything's swimming in water. If we need oxygen from water, no problem. So you put H2O in there to balance any oxygens that need to be balanced. Now, what about the hydrogens? You're going to balance hydrogen by adding H+. This is an acidic solution. Are there hydrogen ions in it? Yeah, there are. Okay, so we're not adding anything that wasn't already there. It just didn't appear in the equation. Then you balance the half reactions with respect to charge. So the sum of the charges on both sides of the equal sign has to be the same. Sometimes it comes out to be 0 on both sides. Sometimes it'll come out to be +2 on both sides. It doesn't matter what it is as long as they're equal. How do we balance that? We add electrons. Get those two half reactions balanced, and then we need to make the number of electrons in those two half reactions the same. And so we'll have to find the least common multiple and do some multiplication so that, if the first half reaction has 5 electrons, the other reaction has to have 5 electrons. And this is because when you have an oxidation and lose 5 electrons, there has to be something that's gaining 5 electrons, the reduction. We don't have electrons just disappearing or appearing. Whatever was there has to be there. Add the half reactions together. If you've done it correctly, the electrons will cancel out, and some of the other things might also cancel out. And then you should always double check. Okay? So those are the rules. Let's do some examples. So this is kind of like shortcut rules, just to remind us what we're supposed to do. So balance this redox reaction. Well, I'm going to skip the first one because we can. Separate it into two half reactions. This is not rocket science. We've got aluminum and we've got copper. So let's just make our first half reaction start with aluminum. And then we're going to say, well, the aluminum, what does that become? Does it become copper? No, that's silly. It's probably going to be aluminum ion, right? So Al3+, aqueous. So we've got that guy and that guy used. And what do we have left? We have copper. We have copper ion and copper, the element. Two half reactions. Okay? We'll balance with respect to mass. Other elements, then oxygen, then hydrogen. These guys are already balanced for mass. We have one aluminum on each side, one copper on each side, nothing to do. Balance for charge. This side has a +3 charge, and that side has a 0 charge. We need to make them the same by adding electrons that have negative charges. So you're going to look at the side that's more positive, this one, and you're going to add some electrons in there. 3 electrons and this +3 charge add up to 0, which matches the other side. In this one, the more positive one is on the other side, and so I'm going to add 2 electrons over here. The 2 electrons and the +2 charge add up to 0, which matches what's on the other side. Okay? So here, if we were assigning oxidation states, then we'd be more aware of which is the reduction, which is the oxidation. We can tell that very easily now because this one is losing electrons, so that's the oxidation. This one's gaining electrons, that's the reduction. We don't actually have to identify those in balancing the equation. Okay, make the number of electrons equal. So this one has 3 electrons and that one has 2 electrons. We need those to be the same number. And we can do that by multiplying the equation by a number. So what's the least common multiple of 2 and 3? 6, right? So 6 is the smallest number that has 2 and 3 as factors. So I'm going to make this 6 electrons. And I'll do that by multiplying everything in here by 2. So 2 of that, 2 of this, multiply this, and I get 6. To make this 6, I need to multiply by 3. So multiply by 3, I get 6, and this is 3, and that's 3. So the top one I did times 2, and the bottom one I did times 3. And now we can add them together. So we're going to add them together. And what should always happen, because we set it up this way, we've got 6 electrons on that side and 6 electrons on that side. And so we can say those cancel out. And then let's copy down what's left. 2 aluminum plus 3 copper is going to give us 2 aluminum ions plus 3 copper atoms. So to verify, check the mass. There's 2 aluminums, 3 coppers, that's all good. And check the charge. The total on this side is 3 times 2 plus 6. And the total on this side is 2 plus 3 plus 6. The charge has to be equal on each side. It doesn't have to be 0. Any questions? Yeah. First we're learning acidic solution, and then we'll learn basic solution. It's just a slight tweak. All right, let's do this one. Separate into half reactions. Just take the first element and give it an arrow, and then, which of the products is the closest to that, is the most similar? Well, it's the H2. And then take the other element, chromium, and this is the chromium ion. Balance for mass. Well, up here we have 1 hydrogen over here and 2 over there, so we need to put a 2 here to balance it. Same as Chem 1A reaction balancing. Here we've got a chromium on each side, we're good. Now we balance for the charge. The total charge on this side is plus 2, and it's 0 on that side. This side's more positive, so we're going to add our electrons over here. We're going to add 2 electrons so that the total charge here matches the other side. In the second half reaction, this side is more positive, so we're going to put the electrons over there. We need 2 of them again, because this is 0. 2 positives, 2 negatives, 0. Make the electrons equal. Oh, they're already equal. How nice. Okay, add them together. Electrons cancel out. Copy down what's left. I tend to keep them just in the same order that they were originally. It doesn't matter, because 2 plus 3 equals 5. 3 plus 2 also equals 5. The order doesn't matter, and even mastering chemistry understands that. Any questions? Yeah.
How does solution being acidic change anything?
That's a a good question. How would the solution being acidic change anything? Well, here we use, we've got H pluses. It's a little harder to see in this one. I think we'll see that in the next one, okay? Any other questions? So both of those were pretty simple. Here, this one's a little more complicated and the little notes are gone, but you have your lecture notes. I'm gonna skip the oxidation state thing. 2 half reactions. So, Fe 2 plus. And then that's going to become Fe 3 plus, because this is very close to that. It's a similar thing, right? We can't have iron ions turning into manganese ions. That just doesn't happen. So here we have our permanganate ion. And over here, we have Mn 2 plus ion. So I've taken all my products and reactants and I've split them up into 2 half reactions. We're going to balance for mass, for the atoms. This one has 1 iron, that one has 1 iron, already balanced. This one's a little more complicated. So we're supposed to do all the elements except for hydrogen and oxygen. This has 1 manganese, that has 1 manganese. Great. Then we're going to look at hydrogen. Well, there aren't any hydrogens. I'm sorry, no, we're going to look at oxygens. There's 4 oxygens here. There's no oxygens on the other side. Like, there's nothing I can multiply, right? What do? We put water in. Because is there water around? Yeah, tons and tons of it. So we're going to put H2O in here. That's a liquid. And so that's going to be our source of oxygen. And so this says we need 4 oxygens, so I need 4 water molecules. So great, I balanced the oxygen, but I created another problem. Now I have hydrogens in there too. I've got 8 hydrogen atoms over here. I need 8 hydrogen atoms on the left side. This is acidic solution, so there are hydrogen ions floating around. There's plenty of them. So we can add H plus over here, and it's not like we're really making anything up. That's already in this solution. We just weren't thinking about it before. We want to do the hydrogen last because, after the oxygen, because we can adjust this one and it doesn't mess up anything else. 8, yes, thank you. Okay. Balanced for mass. Balanced for charge. This side's plus 2. That side's plus 3. Add electrons to the more positive side. If I add 1 electron here, that brings the total charge down to plus 2, matches the other side. Okay? Down here, if I added electrons on the right side here, I'm going to add them on the left here. But let's look at the charges. This side, positive 2. This side, a little more complicated, right? This is plus 8 and minus 1. So plus 7, right? So I have a plus 7 on this side and a plus 2 on that side. So I need to add 5 electrons to make them the same. That's a funny 5. Does that make sense? Okay, thumbs. Got it? Confused? No. Okay, can you ask me a question? Yeah. Yeah. So, originally we had manganese and oxygen and manganese. And in order to balance the oxygen, we have to bring something in that has oxygen. So we brought in the water. So then we were able to figure out, well, I need 4 water molecules to give me the 4 oxygens that are over there, okay? But that brought another element in, hydrogen. And you're like, well, great, we fixed one problem, we made another problem. That's okay. So over here we have a total of 4 times 2, 8 hydrogens. So I need 8 hydrogens over here. I can't add hydrogen atoms or hydrogen molecules because there's probably not any hydrogen gas in this solution. But in an acidic solution, there's hydrogen ions, right? Acid, H+. So we're not like making anything up or creating out of nothing by putting this in here. We're just putting it in here to balance the hydrogens. And so we've got 8 of those. And then the charges, so I'm going to add up the total charges on all the products, and I get +2. And before I add the electrons, I've got +8 from that one, and -1 from this one. And those add up to +7. I need this side to be the same as this side. So I need this to be 5 smaller. So I'm going to add 5 electrons, because with the -5 over here, now this becomes a total of +2. Okay? Thank you for asking. Any other questions? Okay, what's the next step? Make the electrons equal. The top one has 1, the bottom one has 5. The smallest multiple of 1 and 5 is 5. So we're just going to multiply the top one by 5 and leave the bottom one alone. So I'm going to multiply all of these coefficients by 5. That doesn't change that it's balanced. Again, you can do this in different order. I'm just choosing to do this one, and then that one, and then anything else, right? So I've got the iron, the permanganate, and then I put that at the end. It could be first, doesn't matter at all. So then over here, I've got 5 Fe3+. It's pretty messy. Oh my goodness. Plus manganese, plus water. Any questions? Yes? We're going to multiply this one by 5 so that this one has 5 electrons to match the 5 electrons down here. Okay? So this reaction is the oxidation, it's losing electrons. It needs to lose the same number of electrons as the reduction gains, because otherwise we're going to have electrons coming out of nowhere. There's no homeless shelter or animal shelter for the electrons, where if you have extra ones you can just send them to the shelter. And there's no bank where you can go, or library where you can check out electrons if you need them. They have to go directly from one thing to the other. Well, in a battery bank, you still have matching charges, opposite charges within the same thing. And then if you allow the battery to do what it wants to do, it will go to 0 charge. Any other questions about this one? I'm just seeing how many slides do I have to get through today, because I don't want to take too much time on this balancing business. Wait a minute. Okay, do this one on your own. I'm going to walk around and answer questions. So I'm going to go through this kind of quickly. You can check what you've been doing. So 2 half reactions. We're going to have one for the copper and one for the nitrogen and oxygens. We're going to balance for mass. We've got copper and copper. That's balance. Here, we've got nitrogen and we have oxygen. So we're going to look at the nitrogens first. I have 1 nitrogen here and 1 nitrogen there. That's all good. Then I'm going to look at the oxygens. I have 3 and 2. I need another oxygen. So we use water to balance the oxygens. So if I add H2O over there, that brings me the extra oxygen I need, so I have 3. That introduces a different problem. Now we've got hydrogens in here. So I've got 2 hydrogens over there. I need somehow to get 2 hydrogens over here. This is acidic solution. There's a lot of H plus ions. So we can add H plus ions, and we're not like cheating or faking or anything, because those are in the solution. So for electrons, look, identify which side is more positive. This side's more positive. That's where the electrons are going to go. So I'm going to put some electrons over here, and I need this number to be such that all of these charges add up to equal those. So this side's 0. I've got a +2 here. If I want to make this 0, I need 2 electrons. If you have a question, please just interrupt. Down here, the charge is a little more complicated. This side is 0 again, but here we have charges in 2 different places. This is +2, and this is -1. And, you know, there's no shame in actually just writing it down, +2 and -1, so that you can see, okay, well, that adds up to +1. I need it to be 0, though, so I have to add an electron to that side. The next thing is we need the numbers of electrons to be equal. This one has 2, this one has 1. So we want to do it as simple as possible. If I multiply this by 2, the whole thing, still balanced, but I get the correct number of electrons. Okay, so that's great if we have an acidic solution. What if we have a basic solution? There's one extra step. So when we're balancing for mass, we're going to do the elements besides hydrogen and oxygen. We're going to do the oxygen by adding water. We're going to balance hydrogen by adding H+. But in a basic solution, we don't have hydrogen ions floating around. We have hydroxide ions floating around. So we need to neutralize the hydrogen ions. What we're going to do is we're going to add enough hydroxide ions, the same number to both sides, to neutralize the hydrogen ions. So let's do an example of that. Here's in basic solution. You know, just kind of stick the word basic in your pocket and say, I'm going to worry about that in a few minutes. I don't need to deal with it just yet. Same procedure, split them into 2 half reactions. Balance everything but hydrogen and oxygen. So on the top here, I have 2 iodines on that side and only 1 on this side. So I can fix that by putting a 2 there. Not worrying about charge yet. Down here, looking at the manganese first, I've got 1 on each side, that's great. Then I'm going to look at the oxygens. We've got 4 oxygens here and only 2 over there. I need 2 more oxygens. We balance the oxygens by adding water. To get 2 oxygens, I need 2 waters. So now I introduce a problem with hydrogens. So I look over here, there's a total of 4 hydrogens. So over here, I'm going to add 4 hydrogen ions. Am I doing okay so far? Up to this point, it's exactly the same as an acidic solution. But now we have to remember, basic solution. There's not excess hydrogen ions in a basic solution. Basic has base in it, right? Hydroxides. So what we're going to do is we're going to neutralize those hydrogen ions. So we're going to add 4 hydroxide ions, because when I have hydrogen plus hydroxide, what do I get? Water. So this is going to make 4 H2Os. But I had it all balanced, so I can't mess that up. I have to add the same number to the other side. However many hydrogen ions you have, that's how many hydroxide ions you're going to have. Everybody follow that okay? So over here, instead of putting 4 hydroxides and 4 hydrogens, I'm really like, well, I know that that's going to make water, right? So I'm going to say, okay, well, those make water, and so that's the 4H2O, and I moved that up there. So now, this whole thing here isn't there anymore. Okay, thumbs. Get it? Not quite. No way. Okay. Someone who's no way or not quite, can you ask me a question? Yes?
If you have four waters on this side, shouldn't you add more waters to the other side?
That's a great question. So we got 4 waters on this side and 2 waters on that side. Do we need to balance those? No, we don't. Okay, I forgot the liquid here. What we'll do is, if there were 4 here and 2 there, then really 2 of them are unnecessary, right? So we would want to subtract 2 waters from each side to get rid of them, right? Because we don't want extra stuff in there. You can do that at this point if you want to, or you can wait until the end. Okay? So we are going to balance that, but not by like making this into a 4. Okay? Does that help? So should we take care of the waters now, or should we wait till later? Now? Okay. So we have 4 waters here and 2 waters there. So then what we're doing is we're subtracting 2 H2Os from both sides. Why did I pick 2? Because this side has 2. We're not going to have the same substance on both sides. So if I subtract 2, let's move this over. Then I've got 0 waters on that side. And just clean things up a little bit. Here, 4 waters minus 2 waters leaves me with 2 H2Os. So that's what you're doing. You can write it down like that or just do it in your head. So these two canceled two of those. And now if you go through and count everything, you'll see it's still balanced. Okay. Charges. This side is -2, that side is 0. This is the side that's more positive, that's where we're going to add the electrons. So I'm going to add 2 electrons over there so that the right side is -2 and the left side is -2. Then I'm going to look at my other equation. Well, the waters don't have a charge. From this one, I have a -1. This doesn't have a charge. That one's gone. And over here, I've got -4. So the left side is more positive. So what do I need to do? How many electrons do I need? 3. Because adding those 3 electrons, 3 negative charges, and this -1 matches the other side. Any questions about that? Now we add them together. Oh, no we don't. They're not the same. This is 2 and that's 3. I was going to go cancel them out and they don't cancel out. Okay, so we're going to have to multiply by 3 and 2. So the top one needs to be multiplied by 3 and the bottom one needs to be multiplied by 2. And I found I really need to write this over here, otherwise as I'm going through I forget what I'm doing. So this times 3 is 6, this times 3 is 3, this times 3 is 6. Down here I'm multiplying by 2, that becomes 6, this becomes 4, this I'm multiplying by 2, 2, 2, and 8. Now we can add them together. Because I have 6 electrons on the top and I have 6 electrons on the bottom. And so those go away. Copy down everything else. 6 I minus plus 2 MnO4 minus plus 4 H2O. It's going to give me 3 I2 plus 2 MnO2 plus 8 hydroxide ions. If we add up the charges on each side, they're going to be equal. If we count the different elements, atoms, they're going to add up being equal. Questions? So we got one more. I want you to try that one on your own. So I'm going to get started on this. What I've done here is I've got the two half reactions and I balanced them by mass for an acid solution. Right, so I've got the correct number of atoms on each side, but I've got H pluses. It's a basic solution. So I look at the number of hydrogen ions I have, and that tells me how many hydroxide ions to add. I have to add the same number to both sides. because it's balanced right now, and we don't want to screw it up. So I'm going to add 2 hydroxides here and 2 hydroxides over here. Then I say to myself, well, these guys together are going to make 2 H2Os. And you say, oh, well, there's H2O on this side also. There's 1 over here, there's 2 over there. So I'm going to subtract 1 water molecule from each side. So that one goes away, and this goes from 2 down to 1. And that's takes care of all the canceling out. So down here, I have 4 hydrogen ions, and so I need to put 4 hydroxide ions. And I need to do the same thing on the other side. These become 4 H2O. This one doesn't have any H2Os over there, so I don't need to cancel anything out. Charges. So I think this part, this is the new part, and that's the tricky part, right? Anybody have any questions about that? So then charges, this side's -1, this is -1 and -2. So a total of -3 over here. Total of, well, let's see, -2, -1, -1. So I need to add 2 electrons, so -2, so that my charges add up to be the same. They'll be -3 on both sides. On the bottom, here I have -4, -4 and -1. Here I have -2. So I need 3 electrons. So -3 and -2 adds up to -5, -4, -1 add up. I'm going to clean this up just because I can. That's a plus, not a multiple. I need the same number of electrons now, right? I've got 2 up here and 3 down here. So the top one I'm going to multiply by 3, and the bottom one I'm going to multiply by 2. So if I'm multiplying by 3, that gives me 6. This is a 1, so it's 3, 3, 3, and multiplying by 3, 6. Down here, multiplying by 2, 2 times 4 is 8, and this is a 2, 2, 8, and 6. Multiplying by 2. add them together. We got 6 electrons on each side, so those guys cancel out. Now, there might be some other things that cancel out. And you can take care of that while you're adding or after. It doesn't matter, but we're kind of in the pattern of taking care of it as we go along. So I've got 3 waters on that side, and I have 8 waters down here. So if I subtract 3 water molecules from both sides, so this side I'm going to go minus 3 H2O, and this side minus 3 H2O. I don't mess up the balance, right? I had 3 H2Os here, and I'm subtracting 3, and so then this guy goes away. Oops. Okay. Here, I had 8 waters, and I'm subtracting 3. How many do I have now? 8 minus 3 is 5. Okay. Is there anything else that's on both sides? Hydroxides. This side has 6 of them. This side has 8 of them. And if you're thinking, this is really a mess. Yes, it is. It's a big old mess. So I'm going to find the side with the smallest. There's 6 on this side. So I'm going to subtract 6 from both sides. I'm doing that because that'll get rid of the hydroxides on this side completely. So this goes then to no hydroxides at all. And here I've got 8 hydroxides minus 6, leaves me with 2. Okay. So now I don't have any duplicates. So if I just copy everything down, I'll be good. 3 ClO minus, 2 CrOH4 minus, 2 hydroxides. It's going to leave us with 2 CrO4, 2 minus, and 3 chlorines, and 5 H2O. Yeesh. There will be one of those on the exam. Exam 4. Pardon me? How would I include that as an exam question? So what they do in the test bank is they'll say, well, balance this in basic solution, and then they'll say, what's the coefficient on the chromate, and what's the coefficient on, the chromate, and what's the coefficient on the chloride, or something like that. And so if you balance it correctly, you'll say, oh, well, it's 2 and 3. And I'll say, yes, you're correct. So if you want to watch this one step by step, you can go back to the video, right? It'll be posted, and you can watch it.